Good morning, students. Welcome to physics. I'm unexpectedly absent today due to a sick child. So I hope you find this video and you should be watching this video and filling in the blanks of your lecture notes as you watch. Feel free to pause the video anytime you need to fill in extra blanks or anytime you need to catch up. So our intent here in chapter 6 is to understand Newton's third law of motion, and that has to do with forces and interactions. We're actually not going to talk again about vectors because we already understand vectors pretty well. And then finally, we will summarize Newton's 3 laws of motion all at once. So an interaction is between one thing and another. And a force interaction is a pair of forces that act on two different objects. So the key here is that it's one object and a different object that share this interaction. So an example is this person leaning on the wall has an interaction of his hand and the wall. So his hand pushes on the wall and the wall pushes on him. This is a force interaction. Newton's third law of motion states that whenever one object exerts a force on the second object also exerts an equal and opposite force on the first. This force occurs whether the second object means to exert a force or not. It occurs immediately, it occurs every time, and it's never been shown that a force occurs without a reaction. Some folks call this the law of action-reaction. So, if you imagine a soccer player kicking a ball with 1,500 newtons of force, what is the reaction against the player's foot? You must say that the reaction is also 1,500 newtons. So the idea is the foot pushes on the ball with 1,500 newtons, and simultaneously the ball pushes on the foot with 1,500 newtons. The ball, of course, accelerates because it's free to move and it has a smaller mass than the foot and leg of the person. The foot and leg, on the other hand, don't accelerate as much because they have a much larger mass. So the trick to Newton's third law is to separate the idea of action and reaction forces acting on two separate objects, separate from the idea of the effect of those action and reaction forces. The effect is what we observe, which is the acceleration of the object. So action and reaction forces. One force is called the action force. The other force is called the reaction force. They are co-pairs of a single interaction. They always occur together. Neither force exists without the other. They are always equal in strength and opposite in direction, and they always act on different objects. And as I just said, those different objects may have different masses. So the effect we observe of these action and reaction forces is not always, or even usually, equal and opposite. But the force that causes the effect is equal and opposite. So another way to say Newton's third law is, for every action, there is always an opposed and equal reaction. We can imagine a car on the road. The tires push on the road while the road pushes the tires forward. The action is the tire pushing on the road, and the reaction is the road pushing on the tire. One good way to identify action and reaction is to identify the interaction, the two objects that are interacting together. So if I state it as object A exerts force on object B, it's easy to identify the reaction because I just switch A and B. I switch the two nouns. The reaction should be object B exerting a force on object A. Or, for example, if we say the action is the rocket exerting force on the gas, so the rocket pushes the gas out, then the reaction we have to say is the gas pushing back on the rocket. So if you step off a curb, the earth pulls down on you. What's the reaction? The reaction is you pulling up on the Earth, and that's super strange to think about. But because of the enormous mass of the Earth, you don't notice or measure an effect of that reaction force. The effect you notice is on you, the much smaller mass object. And of course, I've just given away the answer to the next question. Why do you not sense the Earth moving upward toward you? So it moves, but it's by an imperceptible amount. The effect is so small, right? The acceleration, force over mass, is so small because of the Earth's very large mass. We don't perceive or even measure the Earth's movement. We certainly perceive and measure our movement because we're so much less massive. So here's the idea in a better graphic, I think. So we have equal forces. The size of the force symbol in this equation is the same. A small mass produces a larger acceleration, and a large mass produces a smaller acceleration. And I would, even if I were drawing this myself, I would draw the masses much different size. And then I would draw the accelerations even, bigger and smaller. So on top, we have a cannonball with a small mass and a large acceleration for the same force, compared to the cannon with a large mass and a small acceleration, but the force is the same. So when a cannon is fired, the accelerations of the cannon and cannonball are different because of what? And you get a cute little video. So you see that the cannon kind of recoils a small amount. Maybe on my screen it's like an inch. And the cannonball is fired and travels in that same time a couple of inches. So why does this occur? And as we've been talking about, of course, we say it occurs because although the forces are equal and opposite on the cannon and cannonball, their masses are quite different. And so the accelerations are correspondingly different. Now we consider an even stranger comparison of masses. So we consider a high-speed bus colliding head-on with a bug. We know that the force splatters the bug. And we want to know which is greater, the force on the bug or the force on the bus. According to Newton's third law, we must conclude that the force on both objects is the same. It's an interaction. The force on the bug due to the car is the same as the force of the car due to the bug. However, the effects of that force are definitely different based on the comparative masses of the bug and the car. Now we consider two people on ice. So this is a more sort of reasonable interaction. Will they move in the same speed in opposite directions if they push on each other? We say yes, because they're of equal mass. So this time, equal and opposite forces cause equal effects, equal accelerations, because the objects have the same mass, and force divided by mass is the same. All right, so a huge help in identifying third law action reactions or in identifying third law effects is to consider a system. So define a system. What objects are we worried about? So we consider a single enclosed orange, an orange on a cart. Why not? So an applied external force, so the red arrow is indicating that the cart is being pulled to the right. So the applied external force causes the orange to accelerate according to Newton's second law, force divided by mass. Now we consider what's causing that force. So apparently this force on the apple or on the orange cart is applied by an apple. Here the action and reaction forces don't cancel because they act on two different objects. The external force by the apple accelerates the orange on its cart. Now we consider the system to be both objects. So we draw a dotted line around both the apple and the orange. The apple is no longer external to the system, it's inside of the dotted line. The force pair, the apple on orange and orange on apple, is internal. So it doesn't cause acceleration of the system. the action and reaction within the system cancel out. And if, for example, the floor is frictionless, so the apple can't get any purchase, there's no external forces, and we expect the apple to just sort of walk in place, pulling or trying to pull on the orange, but the orange pulls back on the apple and nobody accelerates. In real life, however, there is at least some friction between the apple's feet and the ground. But the external force of friction now exerts an external force on the system. The external frictional force, so that red arrow to the right, accelerates both the apple and the orange. So we can consider either the orange by itself or the orange and apple together. If we can identify a force that's external to our identified dotted line system, then we have to conclude that the system accelerates according to Newton's second law. So, will the apple and orange system move at constant speed if the orange loses mass, the apple gains mass, a force equal and opposite to the friction force occurs, or none of the above? The only case that the whole system, if we consider the whole system, accelerates or moves with constant speed is if there's a force equal and opposite to the friction force. Consider a helicopter. When the lift force is greater than the helicopter's weight, so when the force exerted by the air on the blades is bigger than the weight, what happens to the helicopter? We conclude that it moves, not only moves, but accelerates upward. How does a bird fly? The bird's wings push down on the air, and so the air pushes up on the bird's wings and the bird itself, right? So there's this action-reaction force of bird on air, air on bird. The bird accelerates upward, and the air that the bird pushes on accelerates downward. What about airplanes? So airplanes' wings are tilted. They're shaped. It's called the camber of the wings, I think. And we'll talk more about flight later, and I've forgotten some of the terms, but airplane wings are shaped so that they're sort of tilted into the wind. Airplanes also take off and land with a tilt, right? A tilt upward. And so the slightly tilted wings of the airplane wings do what? Do they deflect oncoming air down? Do they deflect oncoming air up? Or neither? They must deflect oncoming air down. The wings push on the air in the downward direction, and the air pushes on the wings in the upward direction. Otherwise, the airplane would not experience that upward lift force. Compared with a lightweight glider or airplane, how would a heavier glider have to push on the air? If we want that heavier glider to accelerate up, it needs to push down with more force. So finally, the summary of Newton's three laws. The first law of motion, which is also called the law of inertia, says that an object at rest tends to remain at rest, and an object in motion tends to remain in motion at constant speed along a straight line path. It's the inertia of the object that keeps it doing what it's already doing. Newton's second law of motion, the law of acceleration, says that when a net force acts on an object, the object will accelerate. The acceleration is directly proportional to the net force and inversely proportional to the mass. Finally, Newton's third law of motion, action-reaction, states that whenever one object exerts a force on a second, the second object exerts an equal and opposite force on the first. Action and reaction. So that concludes the lecture for Chapter 6, and we've now seen all three of Newton's laws. Your lecture notes should be filled in. If you need to review the video, that's fine. I'm also posting the slides on Canvas as usual. The next step is, as usual, to read Chapter 6 and answer the review questions 1 through 18 of the new packet, Chapter 6 practice packet. All of these packets can be found on the counter next to the window by the main entrance to the classroom. I'll also post them on Canvas. And I'll see you all on Wednesday.